All right, let's dive right in. Today, we're exploring a concept from the heart of logic and computer science that's going to sound totally backwards, but trust me, it's fascinating. We're talking about the paradox of efficient unsound proofs.
So, let me ask you something that's going to mess with everything you think you know about logic. What if I told you that taking a wrong step, on purpose, inside a mathematical proof could somehow lead you to the right answer and get you there way, way faster? Sounds crazy, right?
Well, believe it or not, it's very real. This is what logicians call the paradox of efficient unsound proofs. It's a mind-bending idea that totally flips our understanding of what makes a proof correct, and it has some huge implications for how we think about efficiency. So let's break this down.
Okay, so before we can talk about breaking the rules, we've got to understand the rules in the first place, right? So let's take a look at the traditional way proofs are done, the standard, sound path.
Think about a classical proof, maybe one in a system called the Gensen-sequent calculus, or LK. It's like building a perfect brick wall. Every single step, every single logical move you make has to be just right. You start with a solid foundation, an axiom you know is true. You apply a rule, you check it, and you repeat. Every single brick has to be flawless.
And this idea of step-by-step perfection has a name. It's called local soundness. It's basically a micromanager for your proof. It looks over your shoulder at every single step, making sure you're following the rulebook to the letter. This is especially true for these tricky rules called eigenvariable conditions, which are all about making sure you're using your variables the right way. If even one tiny step is off, the whole thing is thrown out. It's super rigorous, it's reliable, but man, it can be slow.
But what if there's another way? A shortcut? A clever little hack that lets you bend those super strict rules but still get to the right answer? This is where our paradox really kicks in.
So here's the revolutionary idea from researchers Aguilera and Bos. They basically asked, what happens if we loosen up a bit? What if we allow individual steps in a proof that, on their own, look unsound because they violate those strict eigenvariable conditions we just talked about?
And to make sure things don't go completely off the rails, they introduced a new kind of safety net called global soundness. See, instead of checking every single brick, it just looks at the whole wall at the end to make sure it's standing strong. It lets you use those kind of messy, locally unsound shortcuts, but with one big rule. Your logic can't chase its own tail. As long as you don't end up in a circular loop, the final proof is considered valid.
So you see the difference here, right? It's a tale of two philosophies. The old way, local soundness, is that slow and steady, perfection at every turn approach. The new way, global soundness, is all about being flexible and efficient. It doesn't care if the steps in the middle are a little messy, as long as the final answer is solid. It's like, stop worrying about every single footstep and just make sure you arrive at the right destination.
Okay, so this is where it gets really, really cool. What's the actual payoff to this new, flexible way of thinking? Well, it's just astonishing. And I want you to pay close attention to the wording here. Non-elementarily shorter. That's not just a fancy way of saying a lot shorter. No. This is a technical term that means the speedup is so ridiculously huge, you can't even describe it with normal math, like, exponents. We're talking about a whole different level of efficiency. And this chart just puts it in perfect perspective. I mean, imagine a proof that used to be 100 pages long. With this new method, which is called LK+, it could be a single page. Just one. That's the kind of compression we're talking about. It's wild.
So, okay, what does this all mean? This isn't just some weird little quirk in logic. It actually points to this bigger theme, a tension that you see all over science and math. So, let's boil it down. What are the big takeaways here? First, there's this powerful trade-off. If you're willing to relax the rules on a local level, you can get these massive gains in efficiency. Second, that word soundness we've been using, it's not so simple. It can be a local thing or a global thing. And finally, in fields like computer science, this hunt for faster, shorter proofs isn't just an academic game, it's a really important goal. And this quote from the research really hits the nail on the head. Sometimes the systems that are the most pure on paper turn out to be extremely inefficient in the real world. It points to this constant tug-of-war between theoretical perfection and practical results. Sometimes you gotta get a little messy to get things done faster.
And that kind of leaves us with this huge open-ended question, doesn't it? This whole idea of trading a little bit of local purity for global integrity and a massive speedup is so powerful. It really makes you wonder, if this works for something as basic as a mathematical proof, where else could we apply it?
What rules in our own jobs or our own ways of thinking are holding us back for the sake of a perfection we might not even need? What's the next rule that's just begging to be questioned?